Welcome back, folks. We're going to start our first circuit theorem today. We have methods of analysis. We've talked about mesh analysis, nodal analysis. We can argue about seat of the pants, whether that's actually a method of analysis. It's not particularly methodical. But we're going to look at our theorems. These three theorems that we're going to look at in this class help us take a complex problem and break it into smaller parts so that we can analyze those smaller parts and then put it back together so that we get an answer. Okay, and that's kind of the essence, in my mind, that's the essence of engineering. How do we take a complex problem, break it into tiny bits, solve those tiny bits, and then put it back together at the end? Okay, so the theorem that I'm going to start out by teaching you today is called superposition. Some of you may have heard the word superposition in some of your other classes. I know I have a lot of MEs that watch these videos, and you might talk about the superposition of forces on a body. We're going to talk about the superposition of sources on a particular voltage or current in the circuit. This isn't a particularly efficient way to analyze a circuit, but there are times where it's the only way you can analyze a circuit. If you continue on in our studies, you may take another course from me, and in that course, I like to say, I not only want you to analyze any circuit, that's what this course is for, I want you to be able to analyze any circuit responding to any signal. And in order to do that, we may have multiple frequencies in that circuit, and that's when we have to use superposition. We introduce superposition here because we have all the tools to do it, and it's a good stepping stone so that you're comfortable with it before you get to that slightly more advanced material. So we're going to do it here. All of the problems we look at here, you can analyze using mesh analysis or nodal analysis, and it's going to be faster. Okay, but we need to do this because we need to do this now when it's simple enough to introduce before we run into it down the road. Okay, it's an important theoretical stepping stone. Superposition can be stated as in this way: any voltage or current in a circuit is the algebraic sum of the voltages and currents caused by each independent supply by itself. Okay, so there's that word algebraic again. We have to consider sign, and we have to break up the problem into what I call subproblems, and we're going to have the same number of subproblems as we do independent supplies in the circuit. Okay, so let's start by looking at an example because I find that's the best way to get this into your brain. Okay, so here's our first example. I know students get stuck, and maybe you do, get stuck on like, what are the steps? Okay, so here are the steps, but there's a lot of variation on how these steps are applied. So we need a lot of examples and we need a lot of experience applying these steps. But for starters, let's look at these 5 steps. We're going to take each independent supply in turn, and that word independent it's there for a reason. We'll deal with dependent supplies in a bit, but that word is there, so I want to emphasize that. We want to replace all other independent sources with their ideal sources, and we haven't talked about ideal sources yet. For now, what that means is their ideal resistances, really. Look at that, I'm editing myself. Resistances. If you're following along in my unedited notes, now you know why they're unedited. Okay, so for a voltage supply, voltage supply, we get a short, a short circuit, just a wire. Think of it as a 0 ohm if you need to. For a current source, we're going to open the circuit. Okay, we're just going to remove the current source. Think of that as an infinite resistance. Okay, replace all other independent sources with their ideal resistance. Okay, voltage supply is a short, current supply is an open. I usually tell you to write that on your cheat sheets because it's important, and getting them backwards gets you the wrong answer. And it's a pretty silly thing to get backwards and just get the wrong answer if you do everything else right. So commit that to memory if you can. Okay, we're going to solve for the desired value. So we got to do some circuit analysis. You can do seat of the pants. You can do mesh. You can do nodal. I'm not going to tell you what to do. I have a pretty strong preference for mesh myself, but I'll mix it up a little bit so that you see everything. People tend to get attached to one method of analysis and stick with it. Mesh, I don't know, for some reason I stuck with mesh. Even though nodal can do op amps, and nodal can do transistors if you go study transistors. You know, there's all sorts of things like that that nodal can do that mesh can't. I'm just wicked fast at mesh. You know, go figure. Solve the desired value. So we're going to use some method of analysis using the polarity and direction marked in the original problem. This is going to keep you honest when you have to add them back together, because then we can just take whatever sign comes out of that analysis and we can just add them all together. Adopt that sign. Do that algebraic summation. We got to repeat this for each independent supply. So arguably 1 and 4 are kind of repetitious themselves. But then once we have all of these little subproblems solved, we just add them back together. Okay, we do that algebraically. So let's do that. How long have I been yapping? 6 minutes? Not bad. I think we can handle this one without making the video outrageously long. Okay, so nice, simple problem. You could probably go seat of the pants on this, although it has 2 sources, so that's a little bit of a wrinkle. You could do mesh, you could do nodal on it, no problem. But you got 2 sources, so you can't just do the, like, what they probably taught you in physics. Shh, don't tell anybody. Break it down to the, like, combine all the resistors, find the current, and then build it back up. That's not going to work for this one because you have 2 sources. So if you wanted to do seat of the pants, you'd actually need superposition. Whatever. Let's do it this way. Okay, so the first thing I'm going to do, I'm actually going to copy the problem. Okay, maybe to even emphasize that it's a copy. Okay, and I'm going to call this subproblem number 1. That's kind of my terminology. If you go talk to somebody else and you like break it into subproblems, they might not know what you're talking about. That's on me. Okay, so we want to find I out using superposition, and I would usually ask you which source you want to pick. We have to pick one of these, and inevitably everybody lands on, well, do the first one first. Doesn't matter which order you do them in, okay? Because we're adding, and adding is commutative. So let's say, okay, what does this source do to this current? And that's what we're interested in. So if I want to figure out what this source does to this current, I've got to take all the other independent supplies, and this is a form of independent supply if you go back and watch the early fundamental videos. So I'm going to remove it, and I'm going to replace it with its ideal resistance. The ideal resistance for a voltage supply, I usually make you repeat this to me. I usually put these little terminals just to be like, hey, I took something out there. That's the ideal resistance of a voltage supply. It's a short. So we just draw the wire. It ends up connecting this node to this bottom node. So strange things can happen when you start ripping components out and then placing other things back in. Right now this isn't too bad. All right, so that's what I meant by remove the other independent supplies, replace it by its ideal resistance. Okay, now I also like to change the notation a little, because this is not I out. This is I out with both supplies in. This is now the first part of I out. So we use a superscript to say, hey, it's the first part of I out. Okay, now we go analyze this circuit. We can analyze it any way we like. And we go find what I out is. Let's see, 30 volts. I could probably do this in my head. I'm not going to do it in my head for you. Let's use one of our methods of analysis. Let me drop out here. You've done enough looking at me today, right? All right, and this is where being able to do the shortcut comes in really stinking handy, right? Because if I say this is I1 and this is I2, right, I can come over here and I can say, hey, this is a 2x2. All right, so let's see. What does I1, I'm writing 2 KVLs, so what does I1 touch? It touches the 10 and the 10. What does I1 share with I2? It's the 10 over here. Moving over to here, we have what does I2 share with I1? It's the 10. And then what does I2 touch? It's these two 10s, so it's another 20. Ooh, nice and symmetrical. Okay, right-hand side, first KVL, I go up 30. Second KVL, there is no voltage supply, so that's 0. And this is going to give me I1 and I2. Okay. So I'm busting out the calculator right now. And it's a 2 by 2, 20, negative 10, 30, negative 10, 20, and 0. Okay, so I get 2 amps for I1, and I get 1 amp for I2. Okay. So with those mesh currents, then I just have to write an expression for the first part of I out. Now you could even come back in here and say that this isn't I1, this is the first part of I1, and this is the second part of I'm sorry, this is the first part. This is the first part of I2. Now, that's okay. It's really not necessary. The analysis for each subproblem has to be completely separate. Okay? So these mesh currents are unique to this subproblem. So we got to be a little careful with that. But let's use these mesh currents to find the first part of I out. So does I1 touch the first part of I out? Yep. And it goes in the positive direction. Does I2 touch the first part of I out? Yep. And it goes in the negative direction. And just plug in these values. So we've got 2 minus 1 equals 1. Okay, so that's a good start. Okay, we know what the 30 volt supply does to the first part of I out. Great. Okay, that's our first subproblem. Now, like I said, these mesh currents and all of this analysis is unique to this subproblem. So I really want you to, in your mind, create a firewall. You don't get to reuse any of this. Okay? Do not reuse any of this for any of the other subproblems. You're going to be tempted to. There are going to be some that you go, it looks similar to the last one. Let me just use the equations. Don't do it. I promise you, don't do it. It's a whole different circuit. Okay. Do I still have the circuit? I do. Cool. So now we do it again. Did I get rid of that up there? Yep. Okay, now we do it again. And we say subproblem number 2. And now we're analyzing the circuit to figure out what VS2 does to I out. Okay, so we play the same game. We get rid of all of the other independent supplies and we replace them with their ideal resistances. The ideal resistance, we'll talk about that more when we get to the next two theorems. The ideal resistance for a voltage supply is a short, so we just draw that as a short. All right, and now this is the second part of I out. All right, completely separate analysis for this one. I1, I2, and we play the same game. We analyze it any way you want. If you like nodal, go ahead and try this with nodal. If you like seat of the pants, well, then you live more bravely than I do. But go ahead and do it. Just get the right answer. Okay. So we have another 2 by 2. It looks like I1 touches the 10 and the 10. So we get a 20 there. I1 shares the 10 with I2, so we get a negative 10. Hey, this is starting to look familiar. Okay, we're going to invert this. I2 shares the 10 with I1. And I2 touches this 10 and 10. Hey, that's all the same. The difference here comes in the supplies on the right-hand side of the equation. Okay, there is no supply over here. And if I'm looking at this one, be careful with your polarity. I'm going around this way. I'm going plus to minus. So it's going to be minus 60 volts. Okay. Solving that. Let's see. solving that, which I already have halfway plugged in. Oh, I'm living dangerously. I'm reusing something, but I think it'll work out. -2 amps and -4 amps. Okay, so we have our mesh currents for the second subproblem. We come back and we do the same kind of thing here where we use those mesh currents to find the second part of I out. Does I1 touch I out? Yes, it does. It goes in the same direction. Does I2 touch I out? Yep, it goes in the opposite direction. And then we just plug in our values. So we've got -2 amps minus -4 amps. Okay, so that's going to be +4 added to that. So we're going to get 2 amps flowing down through there. Okay, 2 amps. All right, ready? We're almost there. We've solved all of our subproblems. So let's put another little wall here. The last thing we do is algebraically sum our results. So this is our second result. Okay, so let's see. I out with no superscript, right? This is I out from the original problem way up there. I out is just the first part of I out plus the second part of I out. Okay, so I think we had 1 amp for the first one. I got to scroll up. Yep, 1 amp plus 2 amps equals 3 amps. Okay, took us a little while to get there, but this is superposition. We break it up by the sources, and then we add them together. We got to do the analysis of the individual pieces. For fun, because we can do it, right? We can check ourselves. We can check ourselves with mesh pretty easily. So let me do that quick, just so that we can say, hey, is that the same result? It's going to be the same result. I1, I2. I'm going to drop out again. And it's still going to be a 2 by 2. And we're going to have 20 for what I1 touches, -10 for what I1 shares with I2, -10 for what I2 shares with I1, 20 for what I2 touches, right? That's all going to be the same. Okay, we go up 30 as we go around I1. We go down 60 as we go around I2. And that's going to give us some other solution. And let me go do that quickly. Solve it, and we get 0, and -3. I actually think it's going to work out. Who would have thought? Okay, so with those mesh currents, I'm just doing this as a check. This isn't part of superposition. With those mesh currents, we can come back and say I out, no superscript because this is the original problem, is I1 minus I2, which is 0 minus -3, also known as 3 amps. Okay, and it matches, huh? So check with mesh analysis. So at least in this case, it looks like superposition agrees. It's going to agree if you do it right. Okay, we need a little more practice. I got to throw some current supplies in there. I got to throw some dependent supplies in there. But this is superposition. Break it up into subproblems, analyze those individual subproblems, add it together in the end, and you're good to go. All right, let's get some practice. Stay tuned and good luck.